The story of consciousness begins not with philosophy or psychology alone, but deep within the machinery of life itself. For most of the 20th century, scientists viewed the brain as a sophisticated but ultimately classical computer. Billions of neurons connected by synapses, firing electrochemical signals in predictable patterns, giving rise to thoughts, feelings, and the illusion of a unified self. Yet as we enter 2026, accumulating evidence from quantum biology forces a profound reevaluation. The processes that make life possible may rely on the same counterintuitive rules that operate at the subatomic scale, and those rules could be the key to why we experience anything at all. Quantum effects were long thought too delicate for the warm, chaotic environment of living cells. Superposition, a particle existing in multiple states until observed. Entanglement, instantaneous correlation across distance. And tunneling, particles passing through barriers they classically couldn't, seemed confined to near absolute zero labs. But nature exploits them routinely. In photosynthesis, excitons in light-harvesting complexes maintain quantum coherence for hundreds of femtoseconds, allowing energy to find the most efficient path to reaction centers with near 100% efficiency. Birds sense Earth's magnetic field through entangled electron pairs in cryptochrome proteins in their eyes, turning quantum spin into navigational cues. Even the sense of smell may involve quantum tunneling of electrons in olfactory receptors, letting molecules vibrate in ways that trigger detection beyond classical shape matching. Now turn to the brain. Microtubules, hollow cylindrical proteins forming the cytoskeleton of neurons, have emerged as prime candidates for hosting quantum phenomena. These structures, built from tubulin dimers, contain aromatic rings and hydrophobic pockets where electrons and vibrations can delocalize. Advanced spectroscopy in recent years has detected coherent vibrations persisting for microseconds in warm biological tissue, long enough, some argue, to influence neural computation. The ORCH-OR model, continually refined, proposes that quantum superpositions in microtubules build across networks of thousands of tubulins until spacetime geometry itself triggers an objective collapse, a non-computable reduction that registers as a moment of conscious experience. Each collapse corresponds to a discrete now, binding disparate brain regions into unified awareness. Anesthetics disrupt these vibrations selectively, erasing consciousness without halting classical firing, suggesting the quantum layer is not optional but essential. This quantum foundation doesn't stop at the skull. If consciousness requires non-local quantum integration to achieve binding and qualia, then the universe, riddled with entanglement and non-locality, may possess analogous properties. Quantum field theory describes particles as excitations of underlying fields pervading all space. Entanglement links distant regions instantaneously. The cosmic microwave background shows patterns from quantum fluctuations amplified during inflation, imprinting the large-scale structure we see today. Some physicists explore whether the universe's total integrated information meets thresholds for proto-consciousness. Not that the cosmos has thoughts like ours, but that awareness emerges wherever sufficient integration occurs, from neural networks to perhaps galactic clusters, or the quantum vacuum itself. Consider entanglement's reach. Experiments confirm it over hundreds of kilometers. Theory allows it across cosmic horizons. In a universe born from a quantum fluctuation, everything might trace back to a single entangled state. Your consciousness, built on quantum collapses in brain microtubules, could be a localized unfolding of that primordial entanglement, a tiny self-referential knot in an otherwise vast web. When you ponder existence, feel wonder at the stars, or experience the mystery of I am, you participate in a process echoing across space-time. Free will finds room in quantum indeterminacy, not random chaos, but genuine openness at the collapse moment. Emerging technologies test these ideas. If quantum biology proves central to mind, it bridges the explanatory gap between matter and experience, suggesting consciousness is not an epiphenomenon, but woven into reality's deepest level. The mind doesn't merely observe the universe. In its quiet quantum way, it helps bring the universe into focus, one aware moment at a time. Black holes captivate because they expose the limits of our understanding. Places where gravity overwhelms all else, time stretches to eternity, and the laws of physics confront their own contradictions. Once theoretical artifacts of Einstein's equations, they now anchor our quest to unify quantum mechanics with general relativity. In 2026, black holes are laboratories for decoding the nature of reality. The event horizon marks the point of no return. Yet Stephen Hawking showed black holes emit radiation from virtual particle pairs, causing slow evaporation and posing the famous information paradox. If a black hole evaporates, what happens to the information? Breakthroughs suggest it isn't lost, but encoded holographically on the horizon's surface, like a 2D sheet projecting 3D depth. This holographic principle suggests our entire three-dimensional universe, with its depth and solidity, might be a projection from information on a distant two-dimensional cosmic boundary. Spacetime itself might arise from entanglement. Everyday objects, even your hand, could be emergent from these quantum connections. Black holes are simply extreme examples of this emergence. Crossing the horizon, you'd experience smooth spacetime, while an outsider sees you freeze forever. Information remains accessible, scrambled in the radiation, but technically preserved. Deeper inside, quantum gravity avoids the infinite density singularity. String theory envisions fuzzballs of vibrating strings, or perhaps bounces where collapse reverses into expansion. Some models suggest black holes connect to baby universes via tunnels. Primordial black holes from the early universe might even constitute the mysterious dark matter. Observations sharpen the picture. Gravitational waves from mergers and direct images of M87 and Sagittarius A testing our quantum-corrected predictions of reality. Imagine approaching a supermassive black hole. Time dilates. Seconds become years. Your information encodes on the horizon, retrievable eons later. Nothing is erased. Everything transforms. Black holes teach us that reality is resilient. Information endures, space-time emerges, and what seems like an end is a gateway to deeper structure. In this holographic cosmos, your existence participates in a grand encoding. The universe doesn't just contain black holes. It may be defined by the principles they reveal.